go to the question. So you've gone through the video. So do you have any question on the video? Can you understand the topic, the content? Any question? No question at all. Kasha, no question. So have you tried the tutorial? Very easy. Okay. All right. So this is about this week and for work. Actually, we will discuss on reactive. And for your information, this topic will be covered or will be asked in your assignment and also your final assessment. Okay. So non-reactive system is normal. Alright, it's normal. But the method, the procedure of the energy balance is still valid lah. Okay, so if you refer to the video I posted, you have two methods actually, energy balance procedure. Energy balance procedure for just a brief through. Energy balance procedure for reactive, you have two method. Heat of reaction method, heat of formation method. Okay, so don't confuse these two methods with that of heat of formation and also heat of combustion to calculate the heat of reaction. Okay, this heat of reaction here. So this heat of reaction here, heat of reaction there. Actually, you can calculate using heat of formation method or heat of combustion method. That is the way, two way to calculate the heat of reaction. But the procedure or the method to solve the energy balance question, you have heat of reaction method, heat of formation method. Okay. So two different things. Alright, so this one is actually being embedded here. Alright, okay. Now if you refer to this one, this is heat of reaction method. Okay, heat of reaction method. Some question you are given the method or the procedure directly in the question. Some question they may ask you to choose of your own. So if you want to choose of your own, there is only two, heat of reaction or heat of formation. You have to state. If not given in the question, you have to state, okay, I'm solving using heat of formation method. I'm solving using heat of reaction method. If it is already mentioned in the question, then it's very clear. Okay. Now if you go to this one, all right, you have iron, ferrum. So this is the reaction. This is the reaction. Okay, you have ferric oxide, solid, carbon solid, being fed at 40 degrees C, and you have two product stream. You have ferrum and also carbon dioxide. Okay, so if you refer to the reaction here, the ferrum produced from the reaction is still in solid form. But you see here, the iron liquid flows. Okay, so this is what coming out of the reactor. Is the product of the reactor. This is the product of the reaction. Okay, so I hope you can differentiate the two. So if you want to draw, okay, if you want to draw, your product will be iron liquid. It's not iron solid. Okay, so if I can show you the drawing, sorry, my drawing is also without the face. So this is supposed to be solid, this is supposed to be solid, this is supposed to be liquid, this is supposed to be, oh sorry, it's not CO2, it's CO gas. Okay, so the solid from the reaction here, from the reaction, the iron is still in solid phase, but coming out of the reactor, it is in liquid phase. Okay, so for this one, this is very straightforward because you have 100% conversion, complete conversion is 100%, and also stoichiometric quantity. Here, stoichiometric quantity. Okay, so your reactant, um, eh, wait, ignore. Okay, so your reactant uh, are fed in stoichiometric quantity. So if it is in stoichiometric quantity, wait, uh, saya besarkan sikit ni. Kenapa pula tak boleh ni? Okay. I should not pin this. Okay. Wait, eh, peliklah sikit ni yang baru ni. Saya pun tak jumpa cari. Okay. Eh, why can't I make any ni? Why can't I draw? I should not pin Unpin your presentation. Okay. Alright, so this is reactant effect in stoichiometry. So what do you mean by stoichiometry? If I have one more here, I should fed 3 more of carbon. Okay, if the basis is not given. But now the basis is already given in the question, 100 mole per second of iron being produced. So if I refer to the drawing, okay, so my N4 will be 100 mole per second. Okay, so this one, 100 mole per second. Okay, so now if it is fed in stoichiometry, and then if I refer to the stoichiometric coefficient of the component or component, so means that for every ion, okay, two from the reaction you should produce 2, but the 2 is represented by 100. So every ion produced actually 50. For every mole is actually 50 mole per second being produced. Okay, 100 divided by 2 lah. Okay, so this is 2, this is half, because this is 1, coefficientnya 1, the coefficient 1, so it's only 50. This is very a straightforward calculation. You can still use the atomic or the extent of reaction. If you can recall your CPP1 or material balance extent of reaction, you can use that. For example, you see here, so this is one way of solving using the extent of reaction method. So I use the ferrum or the iron. So iron in the feed, iron in the product equal to iron in the feed plus 2 extent of reaction because this is product. So my extent of reaction is 50. So you can use the 50 to ferric oxide, to carbon, to CO2. But the one I show you on top here is very straightforward. It's none of the atomic or the extent of reaction because this is for 100% conversion, and according to the stoichiometry you can apply this. Okay, if not, then you should not apply this because this is very confusing. Okay, if only 100% and according to stoichiometry you can follow this method. So these 2 represented by 100, so 3 is 150, 1 coefficient is 50, another 3 is 150. So the flow or the mole balance of this component will be your ferric oxide will be fed 50 mole per second, your carbon will be 150 mole per second, your ferrum being produced in liquid is 100, your CO is 150. Okay, so to calculate the extent of reaction, because this is heat of reaction method, so you need to know the extent of reaction. It's 50 mole per second. Alright, now to calculate the Q, determine the rate of heat transfer to or from the reactor using heat of reaction technique. Okay, so you write the reference state. Okay, so reference state as mentioned in the video is the reactant and the product. Okay, again, reactant and product of the reaction. Okay, reactant and product of the reaction. So if what do I mean by that? Reactant and product of the reaction, I should use very slow. Okay, I should use this, the reaction equation. I should use this as my uh, reference state. The reactant and products of the reaction, not the product of the reactor. Okay, because as I mentioned, the product of the reaction is iron solid, but the product of the reactor is iron liquid. So my reference state must be the reactant and product of the reaction, not the reactor. Okay, so I should refer to the reaction. I should refer to the reaction for my reference state. So that's why if you refer to my solution here, the reference state here is ferrum oxide, solid, or the reactant and the product. That is how to solve the heat of reaction technique, using heat of reaction technique. Okay. Okay. Right, the carbon, the ferrum also in the solid, the CO2 in the gas. Okay, so you follow exactly the reaction. Okay, now you draw the inlet outlet enthalpy table, put in the flow rate, all that, the unknown enthalpy here. So you have 4 unknown enthalpy to be calculated. Okay, so the first enthalpy is on the ferric oxide. Okay, ferric oxide H1. So if you refer to table B2 for the heat capacity, this is the CP for that ferric oxide. This is from table B2. Okay, under C. State-nya C. C, as I mentioned earlier, C is referring to crystal. So crystal can be assumed to be solid. Okay, so this is the CP. Alright, it's just that in this calculation, I'm not showing you this one. I am ignoring this part because actually I do not know how to integrate. It's very long time ago since I took this mathematics, so I can't recall how to differentiate that or integrate that term. Okay, but now I know. So it's just that I'm not have enough time to put in the value of it. That's why I just put in 2 here because I only consider this first term and the second term. This is, if you refer to table B2, this is form 2, from the second form. Form 2. So form 2, it will be, your CP will be A plus BT plus CT minus 2. Okay, and the temperature in Kelvin. Okay, temperature in Kelvin. That's why you see here, I convert it to Kelvin there. Okay. So if you want to use the Cobb's rule, I think personally, if you use Cobb's rule to calculate the CP of the ferric oxide, I will half of the full mark. Okay, because the CP is already there in table, so no need to do any other calculation. Okay, all right. So for H2, H2 is for the carbon. The carbon is also there in table B2, also in form 2. The temperature in Kelvin. So again, I am ignoring the last part because the last term ni, because again, as I mentioned earlier, so the value is 0.2177. For H3, the reference state is ferrum solid. Okay, but the product is ferrum liquid. So you have to do hypothetical process path. You increase the temperature to 1535, refer to table B1, and then you convert the phase to liquid, and then you increase to 1600. So if you refer to table B1, no CP given there, then you have to you have to use Cox rule here. Okay, so Cox rule there for solid 0.026, for liquid 0.033. Okay, two different value because solid liquid. All right, it's supposed to be Cox rule irrefutable. Sorry, this is not B. Which one B10? Which one B8? B8. Okay, Cox rule is B8, right? Cox rule is B8. Cox rule is B10. Sorry, this one supposed to be B8 lah. Cox rule is B10. Yes. Alright, so you put there, you integrate here for the solid. This is heat of melting, 15.1. And this is the integration from 1535 to 1600. So you got 56.505. Okay, for the H3. H4 is because CO, gas 25 degrees C. So as I mentioned, for gas, you can simply use table B8. Okay, gas 25 degrees C. 25 degrees C is the only choice that we have to solve reactive. Okay, no other temperature can be selected. Okay, only 25 degrees C, 1 atm. Okay, so you got 8.17. Let me confirm CO. Yes, 8.17. Okay, so next you have to write the energy balance equation. Simplify any term that is not no value or that can be neglected. And then you got Q equal to delta H. Then you expand the delta H because this is heat of reaction method. So you have this term, extent of reaction multiply with the heat of reaction plus the outlet for the flow rate and enthalpy minus inlet of the flow rate times the enthalpy. So when you put there, make sure the unit is consistent. If mole per second, this is mole per second. This is kilojoule per mole. So you should get kilojoule per second. Okay, make sure you have a consistent unit. That's why the CP here, the Cox rule CP, very slow. Okay, the Cox rule CP here, if you refer to table, dia adalah 26. 26. But 26 is referring to what? Joule. Joule per mole. Degree C. So I already converted this to kilojoule per mole degree C. Because I want to make it consistent with the rest. Because the rest is all in kilojoule per mole. Okay, so when you put in, you will got this 31380.3 kilojoule per second. It's very straightforward. As long as you are able to solve the meter balance, non-reactive meter balance, then the energy balance of that reactive will be very simple. Okay, any questions? Yes. No question.
So far, no.
All right. Now the second question. Okay, second question actually I also do not complete the solution. I don't know why. My solution gone. I actually discussed this question with group 3A this morning. But I don't know. My material balance all gone. I don't know what happened. So sorry for that. I just give you an idea because this one is not 100% completion or 100% conversion. It is 65% conversion, and you have also another one 90% excess of air. So this is basically the material balance lah. Okay, the energy balance 10 marks here is very straightforward. Okay, now the material balance. Okay, so for the drawing, you have sulfur dioxide and oxygen, but in the question you actually react the SO2 with air. Okay, so SO2 and air being fed. Okay, in my case I put it into different stream, SO2 and also air here. If you want to put in one stream, then fine, up to you. Okay, but normally, if any reactant react with air, I put it into two different stream lah. But you can put in one because the temperature is also the same, 450 degrees C, 450 degrees C. So if you put in a stream, still can be accepted lah. Okay, but this one 90% conversion. 90% conversion. And the product of the SO2 here is 1,500 mole per minute. Okay. So you have to use the information given from the conversion. Okay. The conversion, the 65% conversion is referring to SO2, not referring to oxygen. Again, if you recall your CPP1, conversion normally will be implemented or will be referred to the limiting reactant. Yeah, limiting reactant. So in this case, SO2 is your limiting reactant. Oxygen for sure is your excess because mentioned here, 90% excess. Being fed is already 90% excess. So oxygen for sure in excess. So SO2 is your limiting. Okay, so the product of 1,500 mole per minute here is the product from the 65% conversion. Okay, so as mentioned here, 65% conversion producing 1,500 mole per minute of SO3. Okay, so if I have if I supply 100%, okay, just very straight calculation here. If it is 0.65 conversion, you produce 1,500. If I have 100% conversion, I should supposed to have 2307.7 mole per minute SO3. Okay, if I have 100% conversion. So if I refer to the reaction here, if 100% conversion, I should get 2307.7 here. So if you refer to the stoichiometric coefficient, 1 to 1, 1 to 1. Okay, so if 100%, so this is supposed to be the flow of the SO2, 2307.7. You can double check that. Okay, you multiply this 2307.7 with 65% conversion. So if you multiply with 65% conversion, you will get back this 1,500. Okay, so from that, you know 2307.7 mole per minute of SO2 being fed. So your N1 here, your SO2 is 2307.7. Okay. All right. So now you can calculate SO2 in the product here, N5. So what is N5? Anybody? What is N5? What is N5? N5 is unreacted SO2. Okay, you can calculate. There are two ways to calculate whether is 0.35 unreacted from the fat to 307.7, or it is actually 2307.7 is the one you fed, and the one produced SO3 there 1,500 because they're equivalent 1 to 1. So you get same value of 807.7. So this is unreacted SO2. Okay, unreacted SO2. So you're done with N1, N4, N5. Now you left with N2, N3, N6, N7. But N7 and N3 is the same value because nitrogen is just an inert gas, right? So it's just there in the reaction, but nothing happened to the nitrogen. So if you can recall excess, the formula of excess, okay, if I can write the formula of the excess, anybody still remember the formula for the excess? What is the formula? Anybody? Nobody dare to answer. Or you can recall your CPP1, material balance. Percentage excess is there in the textbook, chapter 4, right? Anybody? Percentage excess. If I refer to percentage oxygen excess, those in my class in material balance last semester, we already proved that air excess and oxygen excess is the same. So if mentioned there 90% excess air, it is actually the same as 90% excess oxygen. Okay, so I'm focusing to the oxygen. So if I refer to the oxygen, oxygen fat minus oxygen stoic over oxygen stoic times 100% lah, because pakai percentage. Okay, so how to find the oxygen stoic? Okay, recall your CPP1 reactive. You have to start from your limiting reactant. Your limiting reactant is SO2, 2307.7 mole per minute SO2. You use the ratio 1 mole SO2 equivalent to half mole of oxygen. So the oxygen required is only 11 something. 7.7 divided by 2. 1153.85. So only this amount of oxygen is required. According to the stoichiometry with that amount of SO2. Okay, now it is actually fat with 90% excess. So using the formula here, 0.9 oxygen fat, which is what? Oxygen fat, if I refer to my drawing, is N2. Oxygen stoic, 1153.85 over 1153.85. So I will know, I will be able to calculate the flow rate of the oxygen in the fat with that 90% excess. Plus 1153.85. 2192.3 mole per minute of the oxygen being fed to the system. Now, nitrogen, you know the ratio of oxygen nitrogen in air, 0.21 oxygen, 0.79 nitrogen. So the ratio is 3.7 oxygen will be equal to the nitrogen ratio. Okay, so to get the nitrogen, tak boleh padam ni. Whatever. So N3 is 3.76 times 2192.3. Okay, so this is 8 something, I guess. 3.76. 8243.1. Okay, more per minute oxygen. No, nitrogen, sorry. Okay, so I'm done with the fluid. Any other things? Oxygen, nitrogen. Okay, now I only left with oxygen in the product. Oxygen in the product N6. N6. So what can I do? Recall your CPP1, atomic balance or extent of reaction. So if I want to use extent of reaction, I would better use extent of reaction. Why? Because this is heat of reaction method. So heat of reaction method, I need to know extent of reaction. Okay, it's not wrong to solve using atomic, but later I also need to calculate the extent of reaction. So I better use extent of reaction method lah. So we go to what? SO3. Okay, SO3. Yeah, I'm referring to SO3 because SO3 the flow rate is already given. So SO3 in the product SO3 in the product is equivalent to and SO3 in the feed in the feed dia adalah product. So product is plus extent of reaction. So in the product you have 1500. In the feed 0 because you do not feed SO3. SO3 is your product. So your extent of reaction is 1500 mole per minute. So if I want to do for oxygen, the extent of reaction for the oxygen in the product, which is my N5. Oxygen in the feed, tadi berapa kira tadi oxygen in the feed? 2192.3. Okay. Oxygen is reactant, so minus 0.5 extent of reaction. So what will be the oxygen left? 0.5 times 1500. Plus 2192.3. So you should got 1442.3 mole per minute of oxygen. Okay. So I guess we've done with the material balance. Now you can proceed with the energy balance. Okay. So for the energy balance, as what the energy balance procedure, write the equation and then solve. Lepas tu what? Table. Okay, in the outline table. So we write first the energy balance. EK plus EP. So cancel this. You got this, and then you expand this. Extent of reaction multiply with heat of reaction plus outlet minus inlet. Okay, extent of reaction is already been calculated. Heat of reaction is not yet been calculated. So heat of reaction, so normally kita akan pakai heat of formation method lah. Okay, because heat of combustion method, the value is quite limited in the table. So if you refer to table B1, it will be heat of formation of the SO3 minus heat of formation for SO2. Okay, product minus reactant. Okay, product minus reactant. So SO3 sulfuric. Okay, SO3 is negative 395.18. SO2 minus 296.9. So your heat of reaction will be negative 395.18 plus 296.6. Negative 98.28 kilojoule per mole. Okay, so next what to do? You need to draw the inlet outlet enthalpy table lah. Okay, inlet outlet enthalpy table. You write down all the component SO2, oxygen, nitrogen, SO3. You have no SO3, so you have SO2 in the feed 2307.7. Oxygen is 2192.3. Nitrogen 8243 point something, 0.1. Okay, so H1, H2, H3. In the product you have all. So you have H4, H5, H6, H7. Okay, SO2 in the product is 807.7. SO3 in the product 1500. Oxygen in the product 1442.3. Nitrogen is the same flow rate. Okay, now reference state here is SO2, SO3, and oxygen gas 25 degrees C, 1 atm. Okay, because this is heat of reaction. So heat of reaction is reactant and product as your reference state. So you need to calculate H1, H2, H3 from table B8. This is from table B8 because gas, gas 25 degrees C. This is also table B8, table B8, B8, B8. So you need to calculate this H4, H1, H7 using the CP given in the question here. The CP is already given here. I guess this is for gas lah. CP ni CP for gas. Dia tak mention here, but I think we can use this as gas. Or you can assume the value given in the question is in gas form. So kita kata bolehlah CP guna ni. So for SO2 you integrate 0.399. Better convert this to kilojoule per mole degree C. Okay, because to consistent the unit. So you can do the rest lah. The value of the Q later I will share the value of the Q. But with the explanation, are you able to get through the solution? Any question? Any question?
Oh, Doctor.
No. How about the rest? It's quite difficult to detect who are actually talking because this new
Doctor, I want to ask.
Azhar, yeah. Who are talking? Who are talking now? Azhar ke or who?
Me, Ahmad Ismail.
Ahmad. Okay, because I can't. No, it's not detected. I can. Okay, Ahmad Ikmal. Yes.
When
What is
do
your question?
we use the extend reaction formula again, Doctor?
Extent of reaction formula for this one,
When do we use, Doctor?
Okay, extent of reaction do. If you can recall your CPP material balance, you have two method to solve. No, three method actually to solve material balance reactive. Atomic balance, extent of reaction method, molecular balance. So normally molecular we never use molecular lah because molecular is quite confusing. So atomic and extent of reaction, I will always advise student kalau heat of reaction method, soalan heat of reaction method ni you solve using extent of reaction. Why? Because later you need to have to know the extent of reaction ni. So actually soalan ni pun dah minta you kira extent of reaction method. Okay, extent of reaction. So because heat of reaction, you have to calculate the extent of reaction for you to be able to calculate this. So up to you sebenarnya Ikmal. Nak pakai atomic ke, extent of reaction ke. Kalau pakai atomic, you still need to calculate extent of reaction punya value sebab nak kira dalam, nak masuk dalam formula ni.
Okay, faham, Doctor. Thank you.
Alright, sama. Any other question? If no question, then I will stop here. Next week, we will cover heat of formation method, the other way of solving the reactive energy balance. Okay, heat of reaction, heat of formation. For ODL, we never specify the method. We never specify the method. Up to you to solve the question given using heat of reaction method or heat of formation method. Because this is open, we need to have an open question, so we have to prepare a question that is open, so no specific method. If it is face-to-face question, then it is specified because we want to see how you solve using formation method, how you solve using reaction method. So normally both method will be asked in face-to-face question, but for ODL, we do not specify. So you have to write down the method of your choice lah. The method that is shown in the solution or in the answer. So you have to state anyway. Okay. So if no question, I think that's all. Sorry for not completing us giving you the answer. Hope you can try the rest. It's about what 20% left. So you can calculate the Q from there. Later I will share the value of the Q. Okay, so that's all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Salam, thank you, Doctor.
Sama-sama.
Thank you, Doktor.
Thank you, Doktor.
Uh,